Um, so the first couple parts of number 5, they aren't intermolecular force stuff, but if you want to do it as practice as later in the year before the AP test, this is a gas loss problem. It's also a gas law problem. But we're going to be taking a look at part B because this is the one that has to do with intermolecular forces. So if you take a look at the problem, it gives you a little context. It tells you that HCl is a molecular gas as a pure substance. Basically, what that means is that when HCl is a gas, it just stays together as HCl. But when it is in an aqueous solution, it acts as an acid. So it breaks apart into the cation hydrogen and then the anion chloride. And so for part B, we're looking at when it's an anion. So it tells you that when HCl ionizes, Cl minus ions are formed. And so in this box, they want you to draw 3 water molecules with the proper orientation around the Cl minus ion. And they kind of give you a little, I guess, sideways Mickey Mouse to represent the water molecule. So they don't tell you what's hydrogen and oxygen, but obviously you guys know it's H2O, right? So you kind of figure out what circle represent what element. But I want you guys to take a second to see if you guys can do what the question is asking you to do. You're going to draw 3 water molecules, and you're going to draw them the proper orientation based on what you guys know about intermolecular forces around Cl minus. Okay, so take about a minute or two to do that. If you guys finish early, check with the person next to you, compare answers, and then we'll go over together in about 2 minutes. All right, so let's take a look at the structure of H2O before we start the problem, because that'll kind of help us orient the molecule. Sorry, give me one sec. Okay, so H2O looks like this. You got hydrogen bonded to an oxygen, and then other side hydrogen looks like that. So that kind of tells you which element is going to, or which circle is going to represent which element. The white circle in the middle is going to represent the oxygen, and then the 2 black circles that are connected to it are going to represent the hydrogens. Now, we have to take a look at the polarity of it. Now, if you guys remember, water is going to have a partial negative towards the oxygen, and that means the side with the hydrogens are going to be partially positive. And so if you take a look at the chloride ion, this is negative, and so it's going to be attracted to the partial positives of the hydrogen. So you can orient it just like this. As long as the hydrogen side is facing the chloride side, you're good to go. And again, you can put them in whatever position you want, as long as the hydrogens are facing the chloride and the oxygen is facing away. No, it says to do it with this. If you did the Lewis structure, I guess they'd mark you wrong because they asked you specifically to draw the Mickey Mouses, but as long as you have that idea, you should be fine, yeah. To just do exactly what it tells you in the problem. Yes? No, they would not be touching, yeah. Yeah, they would be attracted together, yeah. All right, any questions on that one? Pretty easy, right? Thought it was a pretty simple question. All right, let's move on to the next one. And so this also came from the AP test from last year. This is number 6. And here we're going to be taking a look at HBr and HF. Okay, so for part A, it asks you to list all the intermolecular forces that are present in the 2 substances. So I'll give you guys about a minute, and I want you guys to write down the intermolecular forces that HBr has and that HF has. Okay, so take about a minute to do that, and then we'll go over together. Okay, so let's take a look at HBr and HF. Now, what is the intermolecular force that pretty much everything has? Yeah, London dispersion. So I'm going to write LDF for both of them. Now, just a heads up, for our class, I'm okay with you guys writing LDF and whatnot. Before the AP test, just write dispersion forces. You want to make it as clear as possible to the graders, okay? Now, let's take a look at HBr. Does it have dipoles? Yes, it does. Because HBr looks like this, and Br is more electronegative than H, and so it is going to have dipole. Okay, let's take a look at HF. Does HF have dipole? Yes. Yes, it does. Because fluorine is the most electronegative, and so it's going to have dipole. Great. Okay, so we got the last one now, which is hydrogen bonding. So let's take a look at HBr. Does this have hydrogen bonding? No, it does not. And the reason why is for hydrogen bonding, hydrogen has to be bonded, remember, to fluorine, oxygen, or nitrogen. Br is not one of these. It does not have hydrogen bonding, but HF does have H bonding. Okay, so there you go. Those are the intermolecular forces present in the two compounds. Okay. All right, any questions about that one? All right, so that's part A. Let's move on to part B. Now that we have all the intermolecular forces, we're going to be analyzing the two substances a little bit more. All right, so it is telling us that they give us the delta H of vaporization, so the enthalpy of vaporization. Basically, how much energy is required to vaporize a mole of this substance for each liquid. So you got HBr, which is 17.3, and HF, which is 25.2. So you guys can see that HF requires more energy in order to vaporize, right? And so it's asking us in part one, based on what you wrote down for the intermolecular forces, why does HF require more energy to vaporize than HBr? Okay, and then for part two, it asks you to actually calculate the amount of energy required to vaporize 6.85 grams. Okay, so I'm going to give you guys about 3 minutes to try this out. The first one is just going to be an explanation based on the intermolecular forces. And then the second part is going to be a little bit of dimensional analysis. I know we haven't done that in a while, so hopefully it's a good refresher. But I'll give you guys about 3 minutes to try those two out, and then we'll go over them together. Okay, so HF is going to have a higher enthalpy of vaporization. Anyone want to share their reasoning, their explanation? Sure.
I said it's greater than that of HBr because HF has hydrogen bonding, which makes the intermolecular force is stronger than HBr when because they have hydrogen bonding and the intermolecular forces are stronger, and we have higher enthalpy of vaporization has hydrofluorine greater HF than HBr.
Yeah, something like that's great. So we can put a concise HF has H bonding. That's the reason why. And then you can just say that H bonding is the strongest intermolecular force, which requires the most energy to break. That's it. Something along those lines. Again, keeping concise would be helpful, but you do want to cover all your bases. Okay, but the big thing is hydrogen bonding. Any questions? AP test is easy, right?
What?
All right, these are questions from the actual AP test. All right. Let's go to part two. For part two, a little bit of dimensional analysis. It's asking you the energy required to vaporize 6.85 grams of HF. So we would start with 6.85 grams of HF. And then you would need to use the molar mass to convert into moles. So you would do, what is that, 1920? Yeah, 20 grams of HF per every 1 mole of HF. And then HF, the enthalpy of vaporization is 1 mole for 25.2 kilojoules. And then your grams would cancel out, moles would cancel out, and you're left with kilojoules, which is exactly what you want. So you just plug it into your calculator, and you should be done. Okay, so 6.85 divided by 20 times 25.2. That's it, 8.631. And then make sure you guys label your number with the unit of measurement, kilojoules. That's it. That's fine. Yes?
How are the how many?
I believe there's 2 long ones and then 5 short ones. We're looking at the shorter ones right now. Yeah. Yeah, as we get closer to the actual test, I'll post all the ones that I have from previous years, and you'll kind of get a good gauge of what the long ones look like versus the short ones. Alrighty, let's move on. Okay, so part C, I'll give you guys about a minute or two to do this as well. So based on the arrangement of electrons in Br and F, you want to write down why the bond length in HBr is greater than that of HF. Okay, so if you guys remember the structures we looked at earlier, this is HBr and this is HF. And the question is asking, why is HBr longer, this bond? Why is this bond longer? Okay. Take about a minute or two to write your explanation. And I think that's the last one. We'll go over together and then we'll have some independent study time. Okay, so I'm sure you guys probably heard it as people were discussing, but hydrogen, if you guys remember, how many shells does hydrogen have? One, because it's in the first row, right? So if we kind of draw a rough sketch of hydrogen, it'd be like this. How many shells does bromine have, though? 4, yeah. So bromine is going to have 1, 2, 3, 4, right? And so remember, bonding happens because electrons in the valence shell are shared, right? So they'd be shared like this. So the distance here would be n equals 1, and then here the distance here would be n equals 4. Okay. Now hydrogen and fluorine, we already know hydrogen is 1. But what about fluorine? How many shells does fluorine have? 2. Okay, so that kind of gives you an idea of the distance between them, right? Hydrogen is still n equals 1, but fluorine is n equals 2, and so the distance is going to be a lot shorter. So as long as you talked about the shells or the energy levels, you should be fine. Yeah.
So when you're talking about like the bond, like you should move it like from the middle.
Yes.
Like from the middle to the
Yeah, exactly. Yeah.
So basically it's shells.
Yeah, pretty much, yeah. The shell is what determines the bond. You can say that, but you'll have to supplement what you mean by that. Yeah. So refer to the shells. Alrighty, guys, and I think that is it. Any questions about that? Hopefully it kind of puts your mind at ease a little bit about the test coming up and the AP test even, hopefully.